Should we be looking into getting the lab kit now, or should we be waiting on that?
It's not available yet. I just heard from the lab manager this afternoon, and yeah, unfortunately, we still don't know when it's going to be available. He's been trying to contact the company, and I mean, the thing is, I mean, every university in the country is trying to get their hands on these things, and so I think they're just up to their necks. So it may be, a week, it may be two, it may be 3 or 4. We don't know yet. So I mean, I'll let you know as soon as I hear.
Okay. There is a link for it on the bookstore, so that's why I was wondering.
Hmm. Well, yeah, I think they just put that in to sort of for it to be ready. But as far as I know, they're not here. I mean, you may contact the bookstore and ask, but don't I don't think they're available yet. At least that's what the department lab manager said. So I would assume he would know first, but maybe that's not the case. Anybody else? Oh dear. Dog drama.
Is it your dog?
Yeah, I got 2 of them upstairs. Whenever anything goes down the street, they have to check it out. Okay, so let's see what we have. I got 34 people. That's a good crowd. So yeah, so I'm going to basically pick up where I left off yesterday, and a lot of the work that we did in the recitation this afternoon, and for the folks who'll be doing it after this class, this will certainly make a lot more sense. The recitation should make a lot more sense to those who are working tonight rather than those poor souls who had to struggle with me this afternoon. So we're going to talk about the difference between atoms, molecules, ions, the different kinds of molecules, and get into the history of chemistry. That's kind of one of my favorite parts of the class, is learning that people were able to figure this stuff out well over 100 years ago, when there was no such thing as a personal computer, and you had to do calculations by hand, and so it took some fairly clever people. I'm not sure I would have been up to the task back then, to be honest. So we left off with the law of multiple proportions yesterday. We talked about, and this comes into the naming of covalent compounds. Now, one of the things you're going to be learning about in the recitation is the difference between covalent compounds and ionic compounds. Ionic compounds, and we'll go more into detail a little bit later, but ionic compounds always have a metal and a non-metal. And the metals are the vast expanse of the periodic table on the left, and the non-metals are the very tiny few elements on the right. And when you add a metal and a non-metal together, the metal loses electrons to the non-metal, and they both become ions. The metal becomes a positive ion, the non-metal becomes a negative ion. That is different from these sorts of molecules. Carbon and oxygen are both non-metals. They're both on the right side of the periodic table. And so they generally, when they interact with each other, they generally do not form ions. But instead of one atom stealing electrons from another atom, both becoming charged, they actually share them. Oh, they're sharing and caring. And so they share electrons. That way they each have the requisite number of electrons they need. Another difference is, oh man, there they go. Another difference is non-metal elements form a lot of different kinds of bonds. They can share a single pair of electrons for a single bond. They can share 4 electrons for a double bond, and they can share 6 electrons for a triple bond, because each pair represents one bond. So if I were to say carbon oxide, and we use ide. I'll just make a note of that here. We use ide here when it's the second part of the compound. The first carbon goes first, and we'll explain why that is a little bit later. Oxide just means that it's chemically combined with something. And so if I say carbon oxide, you don't know what I mean, because we know there is at least two different compounds that can form. Carbon monoxide, where there's one carbon and one oxygen. And we also know that there's carbon dioxide, one carbon and two oxygens. Each one can be formed. And so carbon oxide does not give enough information. Whereas if it's an ionic compound, we know what the charges of the positive ion are going to be. We know what the charges of the negative ion are going to be. And so we can figure out how many of each one there are to balance out the charges. When they're sharing electrons, it's a lot more complicated. So let me erase that. So if we have 100 grams of each compound, for the first one, we get 57 grams of oxygen. And for the second one, we have 42 grams of oxygen, or I'm sorry, 42 grams of carbon. Second one, we have 43 grams of carbon and 27, and yeah, this is confusing the way it's just let out. Compound one, we have 57.1 grams of oxygen, 43 grams of carbon. Oxide two, 73 grams of oxygen, 27 grams of carbon. So the way that lays out, this is what the ratio would be. So there's a 1.33 ratio of mass between oxygen and carbon. For the second one, it's a 2.66 ratio of mass from oxygen to carbon. Notice that the difference between them is exactly 2. And that's what we're saying when we say it's these things are, these compounds come in definite ratios. It's always a whole number. So we never have a molecule with 1 atom of carbon and 2.5 atoms of oxygen. That doesn't occur. We will have a molecule with 2 atoms of something and 5 atoms of something else, but you never have half an atom or a third of an atom or a fifth of an atom. So this ratio always has to be a whole number. And that the fact that that ratio is always a whole number is what led Lord Dalton to come up with his personal atomic theory. I mean, a lot of scientists noticed this when they were doing chemical reactions. When they looked at the products, they always got a definitive ratio of one atom to another, and it didn't vary whenever they measured the amount of element 1 and element 2. It always came in a similar ratio that could be broken down 2 to 1, 3 to 1, 4 to 1, 5 to 2. It was always a whole number, and that made Dalton think that, well, matter must be composed of these really, really small particles called atoms that interact with each other. Now, the atom must be the smallest unit of any element that can participate in a reaction, and that kind of makes sense. And so an element would consist of only one type. All of any kind of element, it doesn't matter what it is, there'd only be one type of atom in there. This was before people realized there were different isotopes. And actually, this was even before the proton, the neutron, or the electron was discovered. So it was just thought of a single type of atom. It would be a really, really tiny particle, and they all react in the same way. It's characteristic of that element, and they'd all be the same, regardless of, if you picked out any atom from an element, they would be identical. Now, more postulates of his theory was atoms of one element must be different from all other elements. So carbon isn't sort of like oxygen, or it's sort of like fluorine that have to be different, completely different. And then when we get to the compound, this is where his idea really came through from the experimental results. A compound would have atoms of 2 or more elements in a small whole number ratio. So this is what I was saying before. You can't have half an atom or a third of an atom or a fifth of an atom or something, because they're indivisible. You can't break them down anymore. They're not atoms anymore. And Dalton realized that too, that you could have a compound, that the ratio would have to be 1 to 1 or 1 to 2 or 3 to 2 or something like that, but you couldn't have half numbers or third numbers or anything like that. And then this relates to what we learned last week about how mass has to be conserved. Dalton realized that atoms aren't created or destroyed during a chemical change. They just rearrange themselves. And so if the example here is that if you have some, excuse me, if you have some copper in the bottom of a container filled with oxygen, eventually that copper will get oxidized and become copper oxide. So here's our copper oxide over here on the right, and it's a different color. It's powdery black solid. I think we all know what copper looks like. Copper's got that sort of shiny brown color to it. That goes away, and then it's replaced with something else that looks entirely different. Now, before the atomic theory came along, it was thought that it's been completely changed, that whatever was there originally has been destroyed and replaced with something else. And in a way that's true, but on the atomic level it isn't, because the copper's still there. It's just now bonded with oxygen where it wasn't before. So at the atomic point of view, nothing's different. It's just now in a different environment than it was before. That was 200 years ago. And like I said, that was before we knew what an electron was, or a proton was, or a neutron was, or the nucleus was, or any of that stuff. And so obviously, you know, chemists and physicists have come a long way at figuring out what the atom looks like. Because at the time, didn't even know what atoms were composed of. Was there anything smaller than it? It was thought there couldn't be anything smaller than it, because it was literally defined as the smallest possible thing you could have would be an atom. So we'll go over some of the key developments, and just what I want you to take away from these is when you look at the experiments that were set up, think about how you would have interpreted them. So I'm pretty sure when I look at some of them, I look at it and go, I don't know if I would have had the same interpretation. And it turns out the person who came up with the original interpretation now is really famous because they turned out to be right. But you can see that some of these experiments were designed really, really well to get a particular result. So this is J.J. Thomson, and he was the original discoverer of electrons. Now, you probably aren't familiar with cathode ray tubes, because these were like, you know, computer monitors and old televisions were made with cathode ray tubes, so like a long time ago. Now we have these lovely flat screen, you know, highly bright screens. But before then, basically what these cathode ray tubes are is, let me sort of point you to what you would do is you would have a piece of metal in here, and you'd expose it to a current of electricity until it became charged. And then a beam of some kind, it wasn't known what the beam was, would go to the length of the cathode ray tube, and it would hit the end of it. And at the end of the cathode ray tube was something called a phosphor or a fluorophore. And what that is that something that lights up. And so when it was struck by these beams, it would light up. And so it was, you see, it was invented around turn of the last century in Germany. And so it worked. The thing is, people didn't really know how it worked. And so Thomson was sort of, playing with one in the lab and figured out by putting these charged plates in. So you put these charged plates in the middle with a positive charge on one side and a negative charge on the other. And by moving them back and forth, he noticed that the beam moved toward the positive charge. And that if he moved the positive charge further away from the negative charge, the beam would follow the positive. And if you moved it closer, moved it further away, the beam would go to where the positive charge was. And by that, he figured out that, oh, is there a question?
No.
Oh, okay, no problem. So because it moved toward the positive charge, he figured out that those particles must be negative, because negative and positive attract each other. And the other thing that he noticed was that regardless of what he put in this source, so this is what we call a source, something that basically is a source of charge. It didn't matter what he put in there. It didn't matter what metal it was or anything he put in there. He got the same particles, and they were charged in exactly the same way. So he figured out that there must be some kind of particle that's shared by all atoms and that they're negatively charged. And he called it an electron, because basically it had an electric charge. And so the electron became a negatively charged particle from the atom, okay? So then, about 10 years later, Robert Millikan figured out how much an electron, what the mass of an electron actually was. Because all that Thomson showed was that there's some kind of particle, probably comes from the atom, and it's negatively charged. They had no idea how big it was or how small it was or where it came from. So Millikan tried to figure out exactly what was the charge on an electron and what was the mass of it. And so what he did was that he had this vacuum chamber. So here's what the vacuum chamber looks like here, with an electrically charged plate at the bottom that's negative. So this is negative at the bottom and positive at the top. And so what he would do is spray incredibly fine drops of oil, like incredibly small, like even finer than an aerosol, so like these incredibly small drops, and then have an X-ray here that would charge those drops. And then what he would do is vary the charge of the plate, the top plate and the lower plate. He would vary the charge until he could get the droplets staying in place. So then he could measure the oil drops staying in place. And so when they stayed in place, he would then measure the charge on the two plates. And he noticed that the same sort of thing that we saw with the ratio of elements, the ratio of two elements, excuse me, in a compound. That if you looked at oil drop A or B or C or D or E, he looked at the charge, and charge we measure in something called coulombs. Don't worry too much about that. That's how much a electrical charge is measured in. But what he noticed is that they were always the multiple of something. They were always the multiple of the same charge. So it was either the multiple of 50 or 100 or 500 or 1,000. They all had a common denominator. And so that common denominator became the charge of the electron. He figured out that they all must have a certain number of electrons. And if I figure out what the smallest charge that can be, that must be the charge on one of them. And found out that it was like a really small charge, as it should be, because it's a really small particle. So the results were the charge was always a multiple, like I said, of a specific charge. And so that's what the charge of a single electron is. You can see it's really, really tiny. And Thomson had shown what the mass to charge ratio is. So just like density, if you know what the charge is, you know what the mass to charge ratio is, you can figure out what the mass is. And so it was worked out that the mass of an electron is exceedingly small. You can see 10 to the minus 31 kilograms, super duper small. And in fact, that turns out to be about 1,000 times less than the mass of either a proton or a neutron, which, remember, it still at this time hadn't been really discovered yet.
So, Professor, the C is the unit of a charge?
Yeah, coulombs. That's a unit of charge. Mm-hmm. So voltage is, if you measure is a difference in charge between two things, and coulomb is like basically the amount of static charge. So if I like rub a, well, I don't have much hair here, as you can see, but if I rub a balloon on what's left of my hair, I leave a static charge, and that I would measure in coulombs. Okay, so it's basically a static amount of electricity. We measure that in coulombs. Okay. So originally, it was thought once the negative charge was discovered coming out of the atom. Obviously, immediately it was thought, well, there must be a positive charge in there too. There has to be, because atoms are neutrally, don't have a charge. Neutral atoms are chargeless. They have no net charge. And so so Thomson suggested, oh, well, this makes a lot of sense, that if you have negative charges that come out of the atom, it's got to be positive charges in the atom. So atoms must look like this. And when you think about it, I mean, it seems ridiculous now, but at the time, it doesn't seem ridiculous at all. I mean, that seems like that's the logical answer, is that positive and negative charges like to be close to each other. We know that, right? I mean, positive and negative charges attract each other. And so if you have 31 negative charges in an atom, got to be 31 positive charges in there, and they stick together, and yeah, makes perfect sense. And so it was sort of called the plum pudding model, because it sort of looked like a pudding with a whole bunch of different stuff in there. Interestingly, and this is a scientist that doesn't really get enough credit because nobody knows him anymore, but Hantaro Nakaoka in Japan came up with the idea that atoms resembled a planet with a ring, where you would have positive charges in the middle and you'd have a ring of negative charges floating around it. As it turns out, he was right. But at the time, that makes much less sense than the two charges being together. Because when you think about it, and even when you think about it now, why would all these positive charges be stuck together in one place? Positive charges don't like to be close to each other. They want to be as far apart from each other as possible. So how is it you could have these strong positive charges all stuck together without it flying apart? And that comes up a little bit later. That is something that physicists are working on constantly to this day. So that came to be the discovery of the nucleus, showed that Nakaoka was right. And this is one of the most famous experiments in chemistry, Ernest Rutherford's experiment with gold foil. Now, gold, you will learn a little bit later, one of the properties of metal is that you can hammer it, right? It's malleable. You can shape it. And gold in particular, you can shape, you can pound it, you can pound till it's exceedingly thin. People have probably seen gold leaf before. If they haven't seen gold leaf, they're sort of aware of it. Gold leaf is so fine that you just sort of go on it and it blows away, right? Even though it's gold, and gold is incredibly dense. You can hammer it so thin that it's only a few hundred atoms thick. And so what Rutherford did was that he took some of this gold foil and put a beam and shot a beam at it. And so this beam is made of alpha particles. And we'll learn, I don't know if we're going to get to radioactivity. We may not do radioactivity. But alpha particles are positively charged. So what an alpha particle is 2 protons and 2 neutrons. It's basically a helium nucleus is what an alpha particle is. And so it was known to be positively charged at the time. It wasn't really known that it was a helium nucleus, but it was known to be positively charged because it was attracted to negatively charged things. So he's got radium in here, and Marie Curie had discovered radium a few years earlier and showed that it decays into alpha particles. And so he had some radium, might even have gotten it from Marie Curie, you don't know, I can't remember. So he has it in a lead shield to protect himself from the radiation, has a hole in it to allow the alpha particles to escape, and then points it at this gold foil. Now, what he was expecting, or what other sort of people were expecting, was that they would just bounce off, right? So these atoms, are really close together, and they're super, super small, and there's not a whole lot of space in between them. So the thought was that the beam, the positively charged beam, would hit this and then sort of bounce off. And what we found that, yes, some of them bounced off, but actually about 95% of them went right through without stopping. And that a very small number bounced back much more than he expected. So the angle of them coming back was really, really sharp. Some of them came directly back toward the detector, and the majority of them bounced back at a very acute angle. So that sort of led him to a couple of explanations of what possibly could be going on. So what's one explanation you think could be going on? Why would most of the beams, most of the particles just go right through it?
The light bends.
But the light didn't bend. It just went right through, straight through. The vast majority of the particles just went right through, like that gold foil wasn't even there.
There's a lot of empty space.
Exactly. Yeah, that was the shattering bit of the experiment. Most of the atom, there's nothing there. The vast majority of the atom is just empty. And so that was a shocking discovery. And the second part of the shocking part of the discovery is that there is in this tiny, tiny part of the atom is very, very dense, and it's positively charged. Because it's positively charged, that causes the angle of it bouncing off to be very steep, because you've got positive charges colliding with more positive charges, so they bounce back with a lot more energy than if it was just a neutral space. And so that led him to think to two conclusions: that there must be all of this empty space in here. So there must be a small nucleus in the middle of the atom that's really, really, really small, and it's positively charged. And most of the area of the atom, there's not much density there, really, really small. And so it was determined that the electron must be negatively charged, that was already found, and it must be outside of what's called this nucleus. And at the time, it was decided that what's in the nucleus must be positively charged, and so they called it proton for positively charged. So the electron has an electric charge, and it's already been considered negative. The opposite of that must be positive, and so it was called a proton. It was a while later when the neutron was discovered, but the first modern model of the atom finally had positive charges in the middle, negative charges around the outside. And these, you can see here, these are the different masses. So a proton and an electron, a proton and a neutron pretty much weigh the same. Like I said, and an electron is about 500, 600 times less. So it doesn't really make up much of the mass of an atom. The vast majority of the mass of an atom is just protons and neutrons.
So, Professor, for neutron, it doesn't have a charge, so it's gonna be close to proton or to electron.
I'm sorry, I couldn't hear you. What
So
about
I think neutron, it doesn't have a charge. So in the atom, it's gonna be close to proton or it's gonna be close to electron.
the neutrons are found only in the nucleus. That's why they have the name neutron. They have the neutron for two reasons. One, it's neutral in charge, and two, it's found in the nucleus. And so it's only found in the nucleus. So protons and neutrons are bound together by what's called the strong atomic force. And it's this strong force that binds the nucleus together. Because like I said a few minutes ago, it shouldn't be. Positive charges shouldn't stick together, but they do. And it's one of the central forces of the universe, the strong nuclear force.
Thank you.
Yep. Yeah, so the size of it, like I said, is about 10 to the minus 10 meters, or we would call it angstroms. 10 to the minus 10 meters is also called an angstrom. So with the nucleus in the middle and electrons around the outside. So the nucleus has two particles in it, at least two, just discovering more all the time, of course. The two main particles we know about, protons and neutrons. One is a positive charge and one does not. And you can see the difference in size. So it's about 10,000 times smaller than the atom. And so this sort of explains nicely why Wood Rutherford shot those positive beams at the really, really thin gold foil. 99.99% of the atom is basically empty. And so, I mean, there's electrons there and they're whizzing around, but they're so small that they don't really represent a whole lot of mass. And so it goes right through them. And then only about 1 in 10,000 particles would hit the nucleus and bounce back. So these are the masses in atomic mass units. I sort of mentioned this afternoon that really all I want you to take away from atomic mass unit is its relationship to the mole. Now, an atomic mass unit, all that means to me is grams per mole. So if I had a mole of protons, it would weigh 1.0073 grams. If I had a mole of neutrons, it would weigh 1.0087 grams. Okay? I try not to think about Avogadro's number too much because it doesn't really tell us anything other than the number of atoms it takes to get to 1.0073 grams. It's a big number, you know, but that's the relationship between atomic mass unit and grams per mole. 1 mole of anything is the amount it takes to equal its atomic mass in grams. Just take that away. So if I have if oxygen molecule is 32 atomic mass units, all that means is that it's also 32 grams in 1 mole. That's what's the takeaway from atomic mass unit. Now, one thing you may notice, there's a difference in mass between the proton and the neutron. And interestingly, that's the mass of an electron. And so it's actually a proton plus an electron that makes a neutron. And we know that because there is a form of radioactivity called the beta particle that is nothing but electrons. And we know that that comes from the nucleus. All radioactivity is based on the nucleus. And when a atom emits a beta particle, it emits an electron from the nucleus, and it changes. It goes from something with an atomic number of n to an atomic number n plus 1. And the reason is you've taken one of those neutrons and you've converted it, so a neutron has gone away, and you've converted it to a proton. And so now the nucleus has one more proton than it used to. And that was the proof that a neutron is a proton and an electron stuck together. Okay? Any questions about that? So you have alpha particles that are positively charged, you have beta particles which are negatively charged, and they're nothing but a beam of electrons. Okay. Let's keep going. So this is part of the recitation we did this afternoon too. Basically, what's the atomic symbol mean? What's the atomic number mean? What's the atomic mass? And so when you see an atomic symbol like this, what it is basically just telling you what's the element, and we put the sign for the element there. So if it's carbon, we put C. If it's magnesium, we put Mg. If it's xenon, we put Xe. And then we write the atomic number, which is the number of protons. So for carbon, that would be 6. There's 6 protons in a carbon atom. Then we would write down the mass number. Now, as I mentioned to the class this afternoon, when we have a symbol like this, we're referring to a specific isotope. Now, what do I mean when I say a specific isotope? What's an isotope? Someone's got to know what an isotope is. We talked about it the other day.
Atoms with the same number of protons but different number of neutrons.
There you go, exactly. So when you look at the periodic table and you see the mass, the atomic mass, it isn't an even number. It's always weird. It's always like for carbon, I think it's 12.011 or something like that. So how come we don't put 12.011 here? I mean, that's the atomic mass. How come we don't put it there? We always put a whole number there. Why is that? We put 12 or 11 or 13 or 14. What does this represent?
The average of all isotopes.
Oh, man. Ladies are on top of it tonight. Yes, indeed. Yes, that is the average mass. And so that represents all the isotopes. So if I took a sample of carbon, it's going to have all the isotopes in it. It's going to have carbon 12, carbon 13, carbon 14. It's going to have all of those in it. But you can tell by the average that the vast majority of it is 12, right? Because the average is really close to 12. So this mass number right here is referring to a specific isotope because we give it a whole number. And so so when we have this particular symbol, X with 2 numbers on the outside of it, we're referring to a specific isotope. It's not any atom of carbon, it's that atom of carbon. or it's this atom of carbon. It's very, very specific. So here, I would write down, let me erase this part. So it would be carbon 12 and 6. So that would tell me that this carbon atom has 6 protons, oops, 6 protons, and it has 12 protons plus neutrons, because that's where the mass comes from. It comes from the number of protons and neutrons in the nucleus. That's where the mass comes from. So the mass number is the number of protons plus the number of neutrons. And the atomic symbol you just find on the periodic table. So any questions about this? Now again, this is for a neutral atom. If it had a charge, someone from this afternoon will be able to tell me where does the charge go? If this is an ion and not a neutral atom, where does that go?
On the right side of the element symbol.
Yeah, up and to the right. So it would go right here. So if this was calcium, for instance, a calcium ion, calcium ions are always +2. And so we would put a +2 there. And so that would tell us that would tell us 3 things. It would tell us the number of protons, it would tell us the number of neutrons, and then this would tell us the number of electrons. So pretty much we would have all the information we needed about that particular atom, because we know, just from the symbol, we know how many protons. From its mass, now we know how many neutrons. From its charge, now we know how many electrons. We would know everything about that particular atom. Very good. So neutral atom has the same number of positive and negative charges. So electrons and protons have to be the same. So in a neutral atom, just remember that there's no charge given. The number of protons is always going to equal the number of electrons. So you don't have to go around figuring out how many electrons it has. If there's no charge given, you assume that the charge is 0. Because if it is charged, you have to have, -1, +2, -3, whatever it is, has to be there top right, okay? And again, mass number, just the number of protons and neutrons. And different isotopes are going to have different mass numbers. And really, that's the only way we can tell the difference between one isotope and another. Chemically, they're identical because they're the same compound. They're the same atom. They're the same element. So they react. Carbon-13 reacts just the same way carbon-12 does. It's the same way carbon-14 does. So there's no way to tell them apart that way. The only way you can tell the difference is by the mass. Now, when an atom does not have the same number of protons and electrons, that's when we call it an ion. That's the only time we call it an ion. So it's either going to have more electrons and be negatively charged, or it's going to have fewer electrons than protons and be positively charged. So anytime protons outnumber electrons, it's going to be positive, right? And anytime electrons outnumber protons, it's going to be negative. And so atoms never change their charge by changing the number of protons. Why not? Someone tell me why. See, it's right here, it says atoms only acquire charge by losing or gaining electrons. Why can't it gain or lose protons? That would change the charge, wouldn't it? Give that a think for a second.
Because protons tell what element it is.
Exactly, very good. Yeah, it wouldn't be the same element anymore. And we know that elements don't change in a chemical reaction. Elements change in a nuclear reaction. When I put uranium in a nuclear reactor, it turns into all kinds of different elements. because it's the nucleus that's emitting particles. And so it's undergoing nuclear change and changing the number of protons and neutrons. And so it's taking on all new chemical identities. But an atom that gains or loses, gains charge or loses charge is still the same atom. It's still the same element. So oxygen, for instance, or let's do chlorine. So chlorine gains an electron generally to become chloride ion. And we say Cl minus is chloride ion. The nucleus has not changed. It's still chlorine. If we added another proton, if we took away a proton to give chlorine a negative charge, it would have a negative charge, but it wouldn't be chlorine anymore. It would be, whatever's on the periodic table to the immediate left of chlorine is what it would be with a negative charge. So yeah, excellent. That is absolutely right. So we call negative charges anions. That's fairly easy to remember because when I think about it, negative and anion, so nion negative, sure, makes sense. So it's an anion. What doesn't make as much sense is that a positively charged atom is called a cation. You're gonna have to come up with your own. I've been searching for a long time to figure out how that makes any sense. But cation, if you can think of a way to, the cat sticks in your head when something's positive. Maybe you really like cats. I have a positive feeling about cats. So that's the only one I've come up with. It doesn't work for me because I like dogs better than cats. But anyway, if you like cats, you're positive about them. That's what a cation is. So if you have a neutral sodium atom, has 11 electrons because it has 11 protons. When it loses one electron, then it gains a charge, and we write it like this. We just put sodium plus, and we say it's a sodium cation, or just a sodium ion, because sodium always becomes a cation. You will never see sodium negative. That doesn't happen. Sodium will, and you'll learn why in a little while, but sodium always loses an electron to become positive. In fact, I can't wait to do that. And that is typical of metals. Metals become cations, and nonmetals become anions. That is pretty much always the case. And so when we write an ionic compound, we put the positive one first and then the negative one second, okay? So symbols. Taking chemistry before, we know we always use symbols. The reason is when you're writing out chemical formulas or chemical reactions, it's a pain to write all those things together. And it makes it really difficult to balance the equation. And you may be wondering why there's some elements of these really weird, like mercury is Hg. What the hell is that? And iron is Fe, and copper is Cu, lead is Pb. You have all these weird things. Well, most of those with weird names or with weird letters, like sodium being Na, most of those elements with really weird symbols were discovered like thousands of years ago. Like sodium has been known forever. Lead's been known forever. Mercury's been known forever. And so they were named usually in Latin or Greek. One of my favorite is lead. Anyone know what the symbol for lead is?
PB.
PB, there you go. PB, which means plumbum. And the reason it's called that is because the original plumbing in Roman times was made from lead pipes, which we know now, not that great an idea. So, who knows how much that hastened the fall of the Roman Empire. But lead was used for plumbing because you can hammer it, you can fix it really easily. You could just take another piece of lead and put it on top of the hole and hit it with a hammer and fixed. So it made it really, really easy to fix plumbing. On the other hand, it also leached off lead into the water. It made you crazy. But, you know, hey, it was a small price to pay, right? So when you have chemical symbols like this, only the first letter is, if it's a two-letter symbol, only the first letter is capitalized. So like HG here, just the H. With PB, just the P. Or sodium, just the N, right? The second one is always lowercase, because sometimes you'll get something like this, and you want to be absolutely certain that this is an element. That's nitrogen. That's oxygen. This is something else. So always, whenever you see a capital letter, that means new element. Okay. So here's some mercury right here. So the symbol just represents mercury. It could be a single atom of mercury, it could be a pound of mercury, it could be a ton of mercury. Doesn't tell you anything about the amount. It just says this stuff right here. That's pure mercury. And if it's anything else, you would add something. If it's mercury oxide or something like that, you would then add O to it. Here's some of the really common ones. So these are, you don't have to really memorize these, but there's going to be some that, you know, they're just going to stick in your head because we're just going to use them so often. Like, for, you know, oxygen, we're going to be using that all the time. Carbon, we're going to be using that all the time. Chlorine, fluorine, hydrogen, iodine, zinc, sulfur, sodium, going to be using that a lot. And so some of these are just going to just sink into your head, even if you don't want them, even if you're fighting them off. You won't be able to help yourself. You're just going to remember some of them. But you can always look them up. That's fine. That's always there. But these are the ones you're going to see over and over and over and over again. Especially if you go into organic chemistry, and you're all going to take organic chemistry one day, right?
Right.
Yeah. So you're gonna be studying carbon chemistry, and that's organic chemistry. I mean, there's a whole branch of chemistry that just has to deal with carbon. That's pretty cool.
I heard organic is the hardest chemistry.
Yeah. Dang. Something's going on. I would, I don't know, I found physical chemistry harder than organic chemistry. Organic chemistry is not that hard.
That's what I keep hearing. PChem is a lot harder than OChem.
Yeah, it's just, if you find math hard, then PChem is hard. If you don't find math particularly difficult, like if you really like physics, you're really gonna like PChem. But who really likes physics, right? Except engineers, and they're all twisted. So, yeah, I mean, organic, you learn. I loved organic because that's really started made me happy. I was doing biochemistry because it made a lot of sense. It teaches you a lot of things about how carbon interacts with other molecules that, you know, establishes why we're here. You know, it's the fact that carbon bonds are hydrophobic, means we can separate the inside from the outside, which means we can make cells, which means we can make people, and you know, so take organic. You won't be sorry you did. Really, really interesting. All right, so we've talked about the atomic mass. Each proton, each neutron has a mass of around 1 atomic mass unit. Great, what is atomic mass unit? So I remember, atomic mass unit, the only way to think about it is how many grams per mole is that, right? Because that's really all that means. So a mole of protons weighs about 1 gram, mole of neutrons weighs about 1 gram, mole of electrons weighs a lot less. So the atomic mass of a single atom is approximately equal to its mass number. Now it's not exact, right? Because protons and neutrons weigh a little bit more. And so that's another reason why the average atomic mass is is always a little bit off, because just even the mass of one atom isn't exactly, like carbon-12 isn't exactly 12. It's a little bit more. And in fact, if we go back to Dalton, we call the mass of one hydrogen atom, so hydrogen, we know has one proton, right, and one electron. And the mass of one hydrogen is 1 Dalton. And so we call, that's where like, Dalton has such, big respect to Lord Dalton, that's what we call the mass. That's how we measure masses in biochemistry. When you measure the mass of a protein, you measure it in Daltons, not in grams. So the atomic mass of a single atom is basically in Daltons also, but we don't talk about it. So most elements exist naturally as a mixture of 2 or more isotopes. There's very few atoms have no isotopes at all. There's a couple, but there's very, very few. And most isotopes are not radioactive either, so you have to worry about that. Like for instance, hydrogen has 2 isotopes. You're probably aware of them. I think we talk about it a little bit later. Hydrogen 1, hydrogen 2, which we call deuterium, and hydrogen 3, which is called tritium. And it's only tritium which is radioactive. Deuterium isn't radioactive. Anyone know what deuterium makes? What we use deuterium for? We call it something heavy.
Heavy water?
Heavy water, exactly. Heavy water is D2O, and D is just 2H2O. We just call that heavy water. Yeah. Very good. So isotopes. We just write, as we sort of learned a little while ago, just put it in the top left-hand corner, what the mass is. And we don't need to put the rest of it on there because we pretty much know that with magnesium, if it's magnesium, we know how many protons it has. We can just look it up. So if we're just talking about the isotope, nothing else, all we do is put the number here. So that tells us magnesium 24. So it's a neutral atom because there's no charge on it. And we know how many protons it has because it's magnesium. And we know what the mass of the nucleus is, 24. This one's 25, this one's 26. So all magnesium isotopes have the same 12 protons, just different numbers of neutrons, okay? So we call this, so when we write them out, when you do your recitation, when we give this a name, we just call it magnesium 24, like that. Just like if you go to the hospital or something, they may inject you with an isotope, and they would call it like iodine 128 or something like that, or whatever isotope they're using in the hospital. So the mass number at the top left-hand corner, atomic number. This tells us the number of protons. A lot of times you just leave it out because it's assumed you would know what it is. And then the charge goes up on the top right hand. Just like we've been saying, the charge goes up in the top right hand corner, okay? Sometimes you omit the atomic number, like I said, because, we know what it is. Oops, clear. Yeah, so these are the 3 isotopes of hydrogen I was telling you about. So the vast majority of hydrogen that exists is just 1, and you can see, look at the natural abundance. When it's 99.99%, I mean, that's pretty much all of it, right? So the vast majority just has 1 proton, 1 electron. So the nucleus just a single proton. Deuterium, however, has a neutron in there. So it's a neutron with a proton, and it's stable also. It is not radioactive. But when you add 2 neutrons, Generally, things that have a high ratio of neutrons to protons are radioactive. So here, the ratio is 1 to 1, and that's chill. Ratio of 1 to 2, that's problematic. And that's nuclear physics, which we are not going to talk about. But I thought you might be interested. That, yeah, once you have too many protons in there, that's when things get dicey. Things start to get radioactive. So if we wanted to figure out what the average mass of hydrogen was, we'd have to take into account the abundance of everything that weighs 1, the abundance of everything that weighs 2, and the abundance of everything that weighs 3. That's how we would calculate it, okay? And there's a calculation like this on the recitation. This is how you do it. So you figure out, you take all the different abundances and you convert from a percent to a number you can multiply with. And how do you do that? How do you convert from 19.9 to 0.199? How do you do that conversion?
You divide 19.9 by 100.
Right, because that's what percent means. Per, and cent, which is French for 100. So it means out of 100. So yeah, we just divide it by 100, absolutely right. So we multiply, so boron, for instance, has 2 main isotopes. 20% of it weighs around 10, and 80% of it weighs 11. And so so obviously the average is going to be much closer to 11 than it is to 10. And the way to calculate it is, that's how much of the total is 10, that's how much of the total is 11, and you just add them together. So fairly straightforward. And anyone tell me what this symbol means? That's a little scary symbol for math. What does it mean?
Sigma, like
Summation notation?
It means what? It's sigma, you're absolutely right. What does it mean?
Some.
Sum, yes, it means sum. It means anything after the sigma, add it together. So anything after sigma means add these together, which means add all of the fractional abundances and all of their masses together. So if I have an atom that has 5 different isotopes, I have to add all 5 of them together, okay? That's all that means. Very good. So let's do a quick one here. So magnesium, we've got 78.7% of it weighs 23.98. We've got 10.13% of it weighs 24.99. And we've got 11.17% of it weighs 25.98. So this is a classic exam question. So don't go to sleep on me. This will be on an exam at some point, I guarantee. Usually on the final. We say, oh my God, we had to remember that? Yeah, you had to remember that. So let's calculate the average mass. All right, so what's the first thing we do?
change the percent to so it's gonna be 0.1117.
Okay, so the first one is 0. So we basically, yeah, we change the percentages to fractions because we can't multiply by a percentage, but we can multiply by a fraction. So yeah, so 0.1117 times 25.98. Okay, what else am I going to add to that?
It changed the other one also from percent to fraction.
Okay, but so tell me what it is. I am old and stupid and need help.
Okay, 1 second. 0.7870.
Okay, what do I multiply that by?
24.99.
Okay, and what's my last one?
Oh, I have 2 magnesium now.
Oh, oops. I think this one's 23, actually. I think this one's the 23.
Yeah, it's 23.98.
Yeah. Okay. So what am I multiplying the 24.99 by?
0.1013.
0.1013. Okay. So who's going to do the math for me? What's the first one?
18.1. No, wait, sorry. I did mine in different order. The first one is 2.901966.
2901967.
966.
Okay. What's the next one?
18.87226.
Is it 15?
18.
18, sorry. 18 point.
It's 87226.
7226, okay. And the last one?
2.531487.
148. Okay, or 9, I guess. Okay, so we're going to add all these together. And what's my sum?
24.305713.
713. Man, love a woman with significant figures. There you go. Excellent. So now, that's our answer. But remember, we need to put units in there. So here's our units. So if you forgot units, you're going to be in trouble. The other thing we're in trouble with now is that's way too many significant digits, right? That's way too many. How are you going to figure out how many significant digits to use?
You only need 4.
Right, so this is 4, that's 4, this is 4, they're all 4, everything's 4, right? So we're going to have to round these, oops, put that back up there. So we're going to have 4.
But isn't it after the decimal? Because of the addition?
Mm-hmm. But this one's going to have 4. This one's going to have 4. This one's going to have 4. All right. So when you look at the 4, this one is 3 beyond the decimal. This one is 2 beyond the decimal. And this one is 3 beyond the decimal. So when we're adding, how many numbers past the decimal can we have?
2?
2, exactly. Just like when you're multiplying 2 numbers, you are basically stuck with whoever has the smallest precision. Like whoever has the fewest significant digits, you're stuck. You can't add any more. When you're adding numbers together, you are basically stuck with whoever has the fewest number of digits past the decimal place. You can't go any further. So we would stop there, and we would round it to 24.31 AMU. Or if you wanted to put grams per mole, that would be fine too. That'd be the mass of magnesium. And you can look that up on the periodic table. See, it should be pretty darn close to that. Hopefully, we haven't screwed it up. Right. So that's how you do that. So, and there's a question just like it on the recitation that you should be able to kill now. Oh, let me clear those. So chemical formulas. We got about 10 minutes. So I'll go like another 10 minutes and we'll answer some questions. So chemical formulas, basically, it's just a collection of atoms. It tells you how they're linked together. So chemical symbols indicate the types of atoms, and then subscripts say how many of each kind there are. So you only use subscripts when you have more than one atom of a given type. So for CO, you don't use 1. Generally, you never use 1 when you're writing a chemical formula, because if it's just CO, the assumption is one atom of carbon, one atom of oxygen. That's just assumed. It's not going to be C2O2. It's not going to be C3O3. It just means, it doesn't mean like the ratio is 1 to 1. It means there's exactly one carbon and exactly one oxygen in that molecule. So that's what a molecular formula gives you. Now, a structural formula gives you more information than that. Man, it's just only, that's when you adopt a police dog, that's what you're going to hear sometimes. So a structural formula gives you the same information, but gives you the additional information of exactly how those atoms are connected, okay? So for instance, clear that. Here's methane. Methane, super common hydrocarbon gas. Why is it a hydrocarbon? Because there ain't nothing there but carbon and hydrogen. So we call it hydrocarbons. Burn hydrocarbons in your car every day, unless you have an electric car. So this is the simplest hydrocarbon, 1 atom of carbon and 4 atoms of hydrogen. So if I just gave you this, you really don't know how they're connected together. It could be this, right? It could look like that. We don't know. Soon, hopefully you'll know exactly why it can't do that. But this doesn't give you any more information. This is the molecular formula. This is the structural formula, and it tells you that the carbon is in the middle, and it has a single bond or a single shared pair of electrons with each hydrogen around it. And we'll learn later on, as we learn more about the periodic table, carbon always makes 4 bonds. Carbon loves making 4 bonds. And it does not like to have extra electrons left over. So carbon will make 1, 2, 3, 4 bonds all the time. Not always single bonds. These are single bonds here. Sometimes carbon will form double bonds. Sometimes carbon will form even triple bonds with additional shared electrons, but always 4. And then here we get even more information. Here we have a ball and stick model. And if we were in the lab, we'd be playing with these. They're lots of fun. They're like playing with Legos. This gives you even more information. Additional information it gives you are the relative sizes of the atoms. Carbon is bigger than hydrogen. So you'd have a fat carbon in the middle and you have little tiny hydrogens around it. It also gives you the shape. And I'll go on about shape in a big way near the end of the course, because molecular shape is extremely important. And so you can see here that the shape of it is what's called a tetrahedron. And that these angles are all the same. They're all 109 degrees, like a tetrahedron would be. And each one of these angles is identical. They're all the same. Now, a space-filling model looks like this. And that basically shows you more or less what we think a methane molecule actually looks like. With their big chubby carbon in the middle and the little hydrogens around the outside. So it shows you the relative size, it shows you the relative positions, and then really where they are relative to each other. So a lot more information than just the structural formula, than just the molecular formula. Now, some elements do not exist as atoms. In fact, a lot of the nonmetals exist as molecules. Metals generally sort of exist as atoms that are bound to each other. And we'll talk about the different bonds. There's ionic bonds, which is one charge interacting with another charge. There's covalent bonds, which is one atom sharing electrons with another. And then there's metallic bonds, where you have all the metal atoms sort of close to each other with electrons just flowing back and forth. That's why metals are such good conductors of electricity, is they constantly have electrons flowing back and forth anyway. So just to add another electron and have it move is really easy for metals to be. But for most nonmetals, they don't exist as single molecules. Like for instance, all of the halogens or halogens, depending where you're from, is the group right next to the noble gases. We call that group 7. And so iodine, oops, let me go back. So iodine, bromine, chlorine, fluorine, all exist as diatomic molecules, as does oxygen, nitrogen, hydrogen. They all share electrons with each other. And then when they come in contact with metals, when these nonmetals come in contact with metals, they steal the electron away from the metal and become negatively charged. Ion becomes iodide, bromine becomes bromide, chlorine becomes chloride, fluorine becomes fluoride. Because all of these molecules would much rather just steal an electron away from a poor unsuspecting metal and become negatively charged than exist sharing an electron with another atom and you're just constantly pulling it back and forth. They're a lot more stable as an ion. And other elements, like sulfur, for instance, exist as an 8-mer, which looks kind of bizarre and sort of looks like this. So that's what sulfur looks like. And you can see it sort of comes in and out of the plane, comes in and out, in and out. And this shape is very important. And so this is the way that, like, most of the time, like if you dig up some sulfur, and I wouldn't recommend it because it interacts with the air to form H2S or hydrogen sulfide, or that rotten egg smell, very, very quickly. So this is what generally it looks like when it's in its most stable configuration, S8.
For sulfate, it's always 8.
When it's by itself.
Okay.
It just means that it's in its most stable form by itself. That's what it will look like. And that's also what these mean. Hydrogen, and we'll get to the most stable configuration when we talk about thermodynamics and heat and that sort of thing. So we need to talk about, like, what is the most stable form of an element that exists. And so the most stable form of an element when it's all by itself is S8, H2, N2, O2, F2. That's its most stable, because an oxygen atom by itself is extremely reactive. That's not stable at all. An oxygen atom all by itself will react with damn near anything. So it is super, super active. And so what it does is it interacts with another super reactive atom. They come together and form a very stable molecule. So that's the most stable form of oxygen by itself, is O2, not O. All right, just do one more. Actually, I'll save empirical formulas for next week. These are kind of fun. Basically, an empirical formula tells you what's the simplest way you could express the ratio of one atom to another one in a compound, and a molecular formula is the actual compound. And we'll go over how to calculate each one when we meet again on Monday. So I'm going to leave it there. So any questions about today or anything else in our last 5 minutes or so? Went through a lot today, covered some actual chemistry. Everyone's overwhelmed. Everyone just wants dinner. That's the problem with having this lecture at 4 to 6. Everyone's hungry.
No, actually, I will wait the lecture when you post it, so I will review everything to find if I have other questions.
Okay, that's good too. Yeah, I usually take Friday, well, to edit, because now I'm going to have a lot of things to edit and then post. So they'll be there by the weekend.
Yeah, so if I have any question, it's gonna be on Monday.
Okay, fair enough. Everyone's brain's full right now, including mine. So yeah, so if that's it, I will, yeah, send me any questions you have. If you want to meet sometime other than regular class time or meeting time, office hours time, just let me know. We can work that out. Okay.
Okay, just one question. Are you respond to email in weekend just if I have quick question in weekend or no?
I'm not going to check it as often, but yeah, I normally check emails on the weekend. Yeah. You may not get an instant reply, but yeah, I do check them.
Okay. Okay, thank you.
That's the problem. I mean, that's the problem with working at home, right? Remember the first job I got had a lot of working at home, and then you find out, oh, that's great. I get to work at home, and then but the bad news is, yeah, you're at home and you're also at work. So always at work, like so that's the good. There's the good side and the bad side. That's a bad side. I don't mind answering emails though.
Will you send us like a notification when all the videos are posted on the YouTube?
Yes. Yeah, there'll be links. I'll put links to them all on Canvas.
Okay, thank you.
Yeah, no problem. All right. Have a good night. Eat well.
Thank you.
Be well, everybody.
Thank you, Professor.
Thank
All right.
you.
Thank you.